Tonight, before you fall asleep, consider two possibilities. The first possibility is this: somewhere out there, around one of the 400 billion stars in our galaxy alone, in a solar system that formed long before our own, on a world that is wet and warm and breathing, something is alive. Not bacteria, not slime. Something that thinks. Something that has looked up at its own night sky, noticed the arrangement of its stars, and wondered whether it is the only thing in the universe doing exactly that. The second possibility is this: there is nothing. Not just in our galaxy, but in all of them. All 2 trillion of them. The universe is 440 sextillion kilometers wide in every direction, has been expanding for 13.8 billion years, contains more stars than there are grains of sand on every beach and desert on Earth. And in all of that space and time and matter and light, only one pale blue world ever sparked to life. Only one mind ever formed. Only one species ever looked up and asked, "Is anyone there?" Both of those possibilities are among the most extraordinary things the human mind has ever entertained. And we do not know which one is true. That is where we are tonight, not at the beginning of an answer, at the beginning of the question, the oldest question our species has ever asked, and the one we are, right now, in this particular decade of this particular century, closer to answering than at any point in the history of human thought. I want to be precise about something before we go any further, because precision is how wonder actually works. The question we are really asking is not whether any life exists elsewhere. Given what we now know about chemistry and planets and the scale of the universe, most scientists consider it very likely that simple life, bacteria, microbes, the quiet chemical machinery of biology, exists in many places. That question, while still unresolved, is becoming less surprising by the year. The question that truly keeps astronomers awake, the one that has a different quality of weight to it, is whether complex, intelligent life exists. Whether, somewhere in the galaxy, another mind has turned its instruments toward the sky and wondered as we are wondering now. That question remains entirely open, and here is the thing that stops you if you sit with it long enough. The silence, on the one hand, is total. In over 60 years of dedicated scientific listening, we have detected no confirmed signal from another intelligence. The sky, as far as our instruments can tell, is empty. Not suspicious, not suggestive, empty. And yet, the math. The math says the sky should not be empty. The math says the conditions for life are not rare. The math says there are more potentially habitable planets in the Milky Way alone than there are people alive on Earth right now. The math says the universe has been running for so long, with so many opportunities, that if intelligence can arise at all, it almost certainly has arisen many times, in many places, long before the Earth had even cooled. So we have the silence, and we have the math, and they do not agree. This is the shape of the question we are going to live inside tonight. Not a clean mystery with a satisfying resolution waiting at the end, a genuine one. A question that science is actively, urgently, beautifully trying to answer and has not yet answered, and may not answer for some time. But a question that has already taught us extraordinary things about the universe just by being asked. And a question that, depending on what the answer turns out to be, will tell us something so fundamental about what we are that no single discovery in human history will quite compare. Let's start at the beginning, not with the answer. With the first night someone decided to actually listen. Science has a habit of beginning quietly, not with a bang, not with a press conference, but with a single person in a specific place making a specific decision that no one around them fully understands yet. The story of how humanity first decided to search for other intelligent life in the universe begins exactly like that, quietly. In a small observatory in the mountains of West Virginia, on the morning of April 8, 1960. His name was Frank Drake. He was 29 years old. He had a radio telescope, a receiver, a recording device, and an idea that most of his colleagues considered, politely, eccentric. The idea was this: If there are other technological civilizations in the galaxy, they almost certainly discovered radio waves at some point in their development. Radio waves travel at the speed of light, pass through the interstellar medium with reasonable efficiency, and can be generated with equipment that any species sophisticated enough to build a civilization would eventually construct. If an alien civilization wanted to announce its existence, or even if it was simply producing radio signals as a byproduct of its own communications, as we do, those signals might be detectable even across interstellar distances if you pointed a sufficiently sensitive telescope in the right direction. Drake pointed his telescope at two nearby stars, Tau Ceti and Epsilon Eridani. Both were similar to our Sun. Both were close enough, roughly 11 light-years away, that if signals were being broadcast at reasonable power, he had a chance of detecting them. He called the project Ozma, after the queen of the fictional land of Oz, a place he noted very far away and very difficult to reach. He had 8 hours on the telescope before it would be needed for other work. He sat down. He turned on the receiver. He waited. Think about what that moment actually was. For the entire history of humanity, for every generation before that morning in 1960, the question of whether we are alone in the universe had been a philosophical question, a religious question, a question for poets and dreamers and late-night conversations. No one had ever made it a scientific one. No one had ever pointed an instrument at the sky and said, "If there is something there, I intend to hear it." Drake had done exactly that. On the first morning, he received a signal. It was strong, regular, and exactly what you might expect an artificial transmission to look like. Drake's heart, by his own account, began to move at a pace inconsistent with calm scientific observation. For a few minutes, possibly 10, possibly longer, he had to consider the possibility that he had just answered the oldest question in human history on the first morning of the first experiment designed to ask it. He had not. The signal turned out to be a classified US military aircraft operating in the area, broadcasting on a frequency his receiver happened to catch. When it passed out of range, the signal disappeared. A perfectly mundane explanation for something that had felt, for 10 minutes, like the most significant event in the history of life on Earth. Drake continued listening for 8 hours. He heard nothing else of note. He returned to the telescope the following morning, and the mornings after that, for a total of about 150 hours of observation across several months. He heard nothing. Project Ozma was, by the conventional measure of its stated purpose, a failure. And yet what Drake had done, the act of it, the fact of it, the sheer intellectual audacity of treating this as a scientific question rather than a philosophical one, changed everything that came after. He had made a decision that quietly rearranged the relationship between science and one of the deepest questions humanity has ever asked. He had said, "We can look. We have instruments. We have method. We have will. Let us look." A year after Ozma ended, in November 1961, Drake convened a small conference at the National Radio Astronomy Observatory in Green Bank. 10 scientists gathered to discuss the problem of detecting extraterrestrial intelligence. It was the first meeting ever held on the subject. Before it began, Drake wrote something on a blackboard to organize the discussion. It was an equation, not a complex one, not one that required a physics degree to understand, a sequence of terms, each representing a single factor that would determine how many communicating civilizations might exist in the Milky Way at any given moment. If you could estimate each factor reasonably, you could multiply them together and get a number. That number, whatever it turned out to be, would be the closest thing science had ever produced to an answer. The Drake equation is one of the most important things ever written on a blackboard. Not because it gives us an answer. It doesn't. Not because it is mathematically sophisticated. It isn't, particularly. It is important because of what it does to the question. It takes a question that had always been vague, are we alone? and turns it into something precise. It breaks the question into its components. It forces you to think about each factor separately, to ask what we actually know and what we are guessing, to separate reasonable estimates from wishful thinking. Here is what it says in plain language. Start with the number of stars in the Milky Way that are being born each year. That number is reasonably well established. Astronomers estimate it at around 3 new stars per year on average. So you begin with 3. Now multiply by the fraction of those stars that have planets. For most of Drake's lifetime, this was the most uncertain term in the equation. We had no direct evidence of planets around other stars. We were extrapolating from our own solar system and hoping it wasn't unique. Today, thanks to telescopes we will come to shortly, we know that planets are not rare at all. Nearly every star that has been examined carefully appears to have planets. The fraction is close to 1. Almost every new star has worlds orbiting it. Now multiply by the average number of planets in each system that could potentially support life. This means planets in what astronomers call the habitable zone, the range of distances from a star where liquid water could exist on a surface. Not too hot, not too cold. The Goldilocks distance. Estimates here vary, but most place it at somewhere between 1 and 5 per solar system. Now multiply by the fraction of those potentially habitable planets on which life actually develops. This is where certainty begins to slip. We have exactly one example: Earth. We don't know if life arising from chemistry is easy or hard, common or vanishingly rare. Estimates range from nearly 1, life arises wherever conditions permit, to something so small it barely registers. Now multiply by the fraction of life-bearing planets on which intelligence develops. Again, one example: us. Now multiply by the fraction of intelligent civilizations that develop technology capable of sending detectable signals into space. And finally, multiply by the average length of time such a civilization continues to produce detectable signals. That last term is the one that quietly does the most work. If a civilization like ours typically communicates for 1,000 years before going silent, whether through extinction or through switching to communication technologies that don't leak into space or through deliberate silence, then the number of civilizations we might detect at any given moment is very small. If civilizations typically persist and broadcast for 1 million years or more, the number becomes very large. Drake ran the equation that November morning with the 10 scientists in the room, each contributing their best estimates. The answers varied wildly. The most conservative estimate produced a handful of civilizations in the galaxy. The most optimistic produced millions. What the equation established, and this is what matters regardless of the specific numbers, is that the question is not unreasonable. The factors that would need to combine for intelligent life to arise are not miraculous. Each one taken separately seems plausible. The universe is large enough, old enough, and chemically rich enough that if each of these factors is even moderately favorable, we should not expect to be alone. The equation did not prove we have company, it proved the question was worth asking. And then, 30 years later, we found the worlds. For most of human history, we did not know whether other stars had planets. Think about what that means. Every single night, for as long as humans have looked at the sky, those points of light in the darkness were entirely mysterious objects. We didn't know if they were surrounded by worlds or utterly alone. We had no way to tell. Our instruments were not good enough, and the problem itself was wickedly difficult. A planet orbiting a distant star is roughly as visible from outside the solar system as a firefly flying next to a floodlight. The light from the star drowns everything else completely. So for thousands of years, the question of whether other stars had planets was purely theoretical. We assumed they probably did, because it seemed unlikely that our own solar system was unique. But we did not know. That changed on October 6th, 1995. Two Swiss astronomers, Michel Mayor and Didier Queloz, announced the discovery of a planet orbiting a sun-like star called 51 Pegasi, about 50 light-years from Earth. They had detected it, not by seeing it, but by measuring a tiny wobble in the star's motion. When a planet orbits a star, it doesn't just orbit, it tugs. The star and the planet both revolve around their shared center of gravity, which means the star moves very slightly toward and away from us as the planet circles it. That motion changes the frequency of the star's light in a way that extraordinarily precise instruments can detect. Mayer and Queloz had built those instruments. They had detected the wobble. They had found the planet. They would eventually win the Nobel Prize for it. What followed was not a trickle, it was a flood. Over the years that followed, more detection methods were developed. The transit method, which measures the tiny dimming of a star's light as a planet passes in front of it, became particularly powerful. In 2009, NASA launched a telescope called Kepler, specifically designed to stare at a patch of sky and watch 100,000 stars simultaneously, looking for transits. Over the following 9 years, Kepler found more than 2,000 confirmed exoplanets, planets orbiting other stars, and hinted at thousands more. Today, in 2026, the confirmed count of exoplanets stands at more than 5,700. That number grows every month. Every few weeks, new announcements add more worlds to the catalogue. And here is the thing about those worlds. They are not all barren, airless rocks. Many of them, a significant fraction of them, orbit their stars at just the right distance for liquid water to be possible on their surfaces. They sit in the habitable zone, the Goldilocks distance. Not too hot, not too cold. Think about that this way. If you took all the potentially habitable worlds currently identified in our galaxy and laid them end to end, which would be a peculiar thing to do, the line would stretch for a distance that makes our solar system look like a backyard. We are not estimating their existence anymore. We are cataloguing them. In April 2026, a team of researchers at Cornell University published a new catalogue of 45 rocky exoplanets in or near the habitable zones of their stars, identified using data from the Gaia Space Telescope and NASA archives. 45 worlds with the right size, the right temperature range, and the right distance from their stars to potentially support liquid water. 45 candidates. 45 doors that may or may not open onto something extraordinary. The lead author of that paper was an undergraduate student, which says something worth pausing on. The question of whether we are alone has become, in the space of one human lifetime, a scientific question that undergraduate students are advancing in peer-reviewed journals. Frank Drake pointed a single radio telescope at 2 stars in 1960. Today we are cataloguing dozens of potentially habitable worlds at a time, systematically, with instruments of breathtaking precision, with a growing community of scientists who treat this as one of the central problems of our era. The nearest of these candidates is a little over 4 light-years away. TRAPPIST-1 is 40 light-years. The Cornell catalogue extends further. We have not run out of candidates. 40 light-years from where you are lying right now, there is a star. It is a small star, much smaller than our sun, much dimmer. If you put it next to our sun, the comparison would be something like holding a candle next to a street lamp. It is what astronomers call an ultra-cool red dwarf. A star so cool by stellar standards that it burns with a faint reddish glow rather than the white-yellow brightness we see in our sky every morning. Its name is TRAPPIST-1. Around that small, dim, reddish star, 7 worlds are orbiting, 7 rocky planets, roughly Earth-sized, circling in tight orbits. They were discovered between 2015 and 2017 using a small Belgian telescope at the La Silla Observatory in Chile, and later confirmed and expanded using the Spitzer Space Telescope. When the announcement was made in February 2017, it was one of the most remarkable planetary discoveries in the history of astronomy. 7 worlds around a single nearby star. 3 of them sitting squarely in the habitable zone. 3 potentially habitable planets within 40 light-years of Earth. Let's spend a moment with what 40 light-years actually means. Light travels at roughly 300,000 kilometers per second. In a single year, it covers about 9.5 trillion kilometers. 40 light-years is approximately 380 trillion kilometers. Our fastest spacecraft, the Voyager probes, moving at around 60,000 kilometers per hour, would take roughly 700,000 years to reach TRAPPIST-1. It is not close. Nothing in space is close, by the standards of human travel. And yet 40 light-years is, by astronomical standards, our immediate neighborhood. TRAPPIST-1 is in the same small corner of the Milky Way that we inhabit. On the scale of the galaxy, which is about 100,000 light-years across, 40 light-years is barely a step from our front door. The most promising of its 7 worlds is TRAPPIST-1e. It is slightly smaller than Earth. It sits in the middle of the habitable zone, the sweet spot where its distance from the star is just right for liquid water to exist on its surface. Recent research published in early 2026 suggests that depending on its atmospheric composition, TRAPPIST-1e could have a global ocean, could, under the right conditions, support liquid water across its entire surface. The word could is doing important work in that sentence, and it is worth being honest about what we know and what we don't. We have not directly observed TRAPPIST-1e's surface. We cannot yet detect its atmosphere with the certainty we need. The James Webb Space Telescope has been studying the TRAPPIST worlds and has begun returning atmospheric data, but interpretation of that data is still ongoing. What we know is the world's size, its orbit, its approximate temperature range, and its position relative to its star. What we do not know is whether it has an atmosphere at all, whether that atmosphere has the right composition to maintain liquid water, and whether anything on its surface has ever moved of its own will. Here is something strange about TRAPPIST-1 that is worth holding in your mind. Because the star is so small and dim, the habitable zone sits very close to it. TRAPPIST-1e completes an orbit in about 6 Earth days. A year on TRAPPIST-1e lasts less than a week by our measure. The innermost planet completes its orbit in about 1.5 Earth days. These are not the slow, stately orbits of our solar system. These worlds move quickly, pulled close to a small, faint fire. And because they are so close to their star, most of them are probably tidally locked. One side always faces the star, one side always faces away. One hemisphere in permanent noon, one hemisphere in permanent midnight, with a narrow twilight ring between them where temperatures might be somewhere in the middle. Think about what it would be like if you were standing on TRAPPIST-1e, which I acknowledge is a somewhat speculative exercise. The star would be visible in the sky, but it would look different from our sun. Larger, apparently, because you are closer to it, but dimmer and reddish. The sky might be permanently lit on one side, permanently dark on the other. If there is weather, it would be driven by that extraordinary temperature gradient. If there is an ocean, it might circulate heat between the warm side and the cold side in patterns unlike anything we know. We have no idea if anything lives there, but we know it is real. We know its size and its orbit and its position. We know it sits in a zone where the conditions we associate with life are not impossible. 40 light-years away, and it is only one of 45 recent candidates, only one of more than 5,000 confirmed exoplanets. The catalogue of possibilities is not shrinking, it is growing every single month. Life, as far as we know, is a chemistry problem, not a mystical one, not a miracle. A chemistry problem. Specific molecules combining in specific ways under specific conditions to produce specific outcomes. The outcome in our case being reproduction, metabolism, response to environment, evolution over time. The chemistry is staggeringly complex, but it is chemistry. The same atoms that make up everything else in the universe, hydrogen, carbon, oxygen, nitrogen, organizing themselves into extraordinary structures under the right conditions. And here is the thing about those atoms and those molecules. They are not rare. Carbon, the backbone of every living thing on Earth, is the fourth most abundant element in the universe. It is produced in the cores of stars and scattered when those stars die. Hydrogen is everywhere. Oxygen is everywhere. The basic atomic ingredients of biology are among the most common substances in existence. More than that, complex organic molecules, the kind that are the precursors to life, the kind that begin to approach biological chemistry, have been found in some of the most inhospitable environments in the cosmos. In the gas clouds between stars, in the tails of comets, in asteroids drifting through the solar system for billions of years. In 2023, scientists analysing a meteorite that fell in Murchison, Australia more than 50 years earlier confirmed the presence of amino acids, the building blocks of proteins, that had formed in space long before the meteorite reached Earth. Those molecules were not made here. They were made somewhere out there in the cold between the stars and delivered to our world wrapped in a rock, travelling at orbital velocity. The universe, it turns out, is full of the stuff life is made from. And then, in the week of this recording, NASA's Curiosity rover, which has been driving across the surface of Mars for more than a decade, moving at about 200 meters per day across the rusty floor of Gale Crater, announced a discovery that stopped scientists in their tracks. The rover had found, within the Martian rock it was drilling and analysing, a diverse mix of organic molecules, not just one or two. A varied, rich chemistry, including chemicals that on Earth are considered among the building blocks of life. Mars today is cold and dry. Its atmosphere is thin. Its surface is bathed in radiation. By the standards we associate with life, it is not an inviting place. But Mars was not always like this. 3 to 4 billion years ago, Mars had liquid water. It had a thicker atmosphere. There is strong evidence, and we will come back to this, that it may have had oceans. The Curiosity discovery of organic molecules in rocks that may be billions of years old suggests that the chemistry that leads to life was present on Mars at the same time that life was beginning on Earth. Whether that chemistry went anywhere, whether it ever organized itself into something that was alive, we do not know. That is the question. But here is the point. The ingredients are not the miracle. They are common. They travel through space on rocks. They form spontaneously in gas clouds. They appear on Mars, in meteorites, in the tails of comets. The universe does not seem to be withholding the raw materials. Think about it this way. Imagine you found every ingredient for a specific dish scattered across a vast kitchen. The flour, the eggs, the butter, the sugar, in quantities large enough to fill a warehouse. The question of whether the dish has been cooked somewhere in that kitchen is not answered by counting ingredients. But the abundance of the ingredients does tell you that the kitchen is, at minimum, well stocked. The gap between chemistry and life is real, and it is the question. But the chemistry is there. It is abundant. It is old. It has been running in various combinations across vast regions of space for billions of years. And yet, we have found no life beyond Earth, no confirmed signal, no unmistakable sign, not even a microbe, not even a fossil. The kitchen is stocked, but nobody seems to be cooking. Or, and this is the question that begins to live in you, nobody seems to be cooking anywhere we have looked. The silence has a name. It is called the Fermi Paradox, and it arrives with a story so brief and so human that it has lodged itself permanently in the history of science. The year was 1950. The place was Los Alamos National Laboratory in New Mexico, the laboratory where the first atomic bomb had been designed just 5 years earlier, now humming along as a center of theoretical physics. 4 scientists were walking to lunch together. The conversation, as it often did among physicists at Los Alamos, had drifted towards something absurd and interesting. In this case, the recent spate of newspaper stories about unidentified flying objects. The 4 men were laughing about it, joking about the illogic of the reports. Then they sat down for lunch. and the conversation moved on to other things. And then Enrico Fermi, one of the most important physicists of the 20th century, the man who had built the first nuclear reactor, a man whose mind operated at a level most of his colleagues described with something approaching awe, went quiet for a moment. And then he said, "But where is everybody?" The table, by all accounts, immediately understood what he meant. Here is the logic Fermi had run in his head, probably in the time it took to walk from one side of the cafeteria to the other. The Milky Way is about 13 billion years old. Our solar system, by contrast, is about 4.5 billion years old, which means there are stars in our galaxy that formed 8 or 9 billion years before our Sun. If any of those older stars have planets, and we now know many of them do, and if any of those planets produced intelligent life, and if that intelligent life developed technology, then it had a head start on us of billions of years. A civilization that is just 1 million years more advanced than us would have had time, at sub-light speeds, using reasonable assumptions about spacecraft technology, to colonize the entire Milky Way. Every star, every planet, every corner of the galaxy. 1 million years is not long by cosmic standards. Chimpanzees were roaming the forests of East Africa 1 million years ago. And yet, given the technology we now possess, we could, if we chose to, reach every star in the galaxy within 1 million years of sustained effort. An older civilization would have done this long ago. Their signals would fill our sky. Their probes would be in our solar system. Their presence would be, by any reasonable analysis, unmistakable. And yet, we have found nothing. Our radio telescopes have been listening for 60 years. We have scanned millions of frequencies. We have watched the sky in every band of light we can detect. We have looked for the waste heat of interstellar civilizations, for the signatures of megastructures, for the chemical fingerprints of terraforming. Nothing. Not a whisper. Not a blip. Not an anomaly we cannot explain in terms of perfectly ordinary natural processes. The universe is approximately 14 billion years old. It contains 2 trillion galaxies. It has had, by any reasonable accounting, enough time and enough opportunity to produce intelligence not once, but countless times. And the sky is silent. That is the paradox. Not a paradox in the strict logical sense. It does not involve a formal contradiction. It is a paradox in the older sense, a situation that appears deeply, troublingly wrong given what we know. The numbers say the universe should be teeming with life. The observations say it appears to be empty. Something is off. Let that settle for a moment, because this is not a small discomfort. The Fermi Paradox is one of the most important unsolved problems in science, and unlike many unsolved problems, it has implications that are deeply personal. Whatever the answer is, and we will come to the possible answers shortly, it has something significant to say about the nature of intelligence, the fate of civilizations, and the significance of being alive in this particular moment of the universe's history. Fermi asked his question over lunch in 1950 and then apparently changed the subject. He died 4 years later. The question has been with us ever since. And then, in the summer of 1977, we almost heard something. The Big Ear radio telescope was not a glamorous instrument. It sat on the campus of Ohio State University, a large flat structure that looked less like an observatory and more like a very large piece of agricultural equipment. It was not the biggest or most sensitive telescope of its era. It had no famous discoveries to its name. It ran on a modest budget, staffed largely by volunteers, scanning the sky in a systematic pattern as part of a long-running SETI program. On the evening of August 15, 1977, it was doing what it always did: scanning, recording, printing output onto sheets of paper that would later be reviewed by a graduate student named Jerry Ehman, who had volunteered his time to go through the data by hand, looking for anything unusual. The telescope scanned a region of sky for exactly 72 seconds at a time, limited by the rotation of the Earth. It could not track a fixed point. It swept past. 72 seconds was all it could give anything. A few days later, Ehman was going through the printout. The telescope's output was encoded in a system of numbers and letters, each representing the strength of the radio signal being received at that moment. Ordinary cosmic background noise produced low numbers. 1, 2, 3. Nothing interesting. Ehman turned a page, and there, in the middle of a long stretch of 1s and 2s, was a sequence that made no sense. 6EQUJ5. In the encoding system the telescope used, that sequence represented a signal that rose rapidly in strength, peaked at a level 30 times above the background noise, then fell away again. Exactly as you would expect if a powerful narrowband radio source had passed through the telescope's field of view. Exactly as you would expect from a natural object appearing to rise and fall as the Earth rotates. But it was not at a frequency you would expect from a natural object. It was broadcasting at 1420 megahertz. That number matters. 1420 megahertz is the frequency at which neutral hydrogen, the most common atom in the universe, naturally emits and absorbs radio waves. It had been proposed years earlier as the most logical frequency for any interstellar communication attempt. If you were trying to get the attention of any civilization sophisticated enough to do radio astronomy, you would broadcast at the frequency every radio astronomer already listens to. The hydrogen frequency, the universal dial. Jerry Ehman stared at the printout. He picked up his pen. He circled the sequence. In the margin, next to the circle, he wrote a single word: wow. The wow signal, as it has been known ever since, has never been detected again. Not by Ehman, not by the Big Ear, not by any other telescope, at any time, in any direction. It has been searched for extensively, repeatedly, with instruments far more sensitive than the Big Ear ever was. In 1987 and 1989, the Big Ear searched the same region of sky for hundreds of hours. Nothing. In 2020, a team used one of the most powerful radio telescopes on Earth to search for it specifically. Nothing. 72 seconds. Once. And then silence. We do not know what the wow signal was. That sentence deserves to be said plainly, without qualification. We do not know. Several natural explanations have been proposed over the years: a comet's hydrogen cloud, terrestrial radio interference, an unusual natural radio source. None of them fully accounts for the specific characteristics of the signal. None of them fully satisfies. The honest answer is, it might have been a natural phenomenon we haven't fully characterized yet. It might have been instrumental error of a kind we haven't identified. It might have been something stranger. And this is the possibility that gives the whole story its weight. It might have been exactly what it appeared to be. A narrow-band radio transmission at the hydrogen frequency, originating from beyond our solar system, with a signal strength that implies a transmitter of extraordinary power. We simply do not know. What we do know is this: the wow signal remains the strongest candidate for an extraterrestrial radio signal ever detected. After more than 40 years of searching, it has not been surpassed, not explained, not duplicated, not dismissed to any scientist's complete satisfaction. 72 seconds of something, then nothing. The silence after the wow signal is itself a kind of data. What it means is the question we live inside. Here is a question that tends to arrive quietly and then refuses to leave. What if we are looking in the wrong way? Our search for extraterrestrial intelligence has been from the beginning shaped by assumptions. We assumed that other civilizations would use radio waves because we use radio waves. We assumed they would broadcast at the hydrogen frequency because that is what we would do. We assumed their signals would look a certain way, narrow-band, structured, clearly artificial. But those assumptions are based entirely on ourselves. Radio communication, as a technology, has been in widespread use on Earth for roughly 140 years. In the cosmological context, that is not even the blink of an eye. A civilization 1,000 years more advanced than us, to say nothing of 1 million years, might have moved through radio communication and out the other side as thoroughly as we have moved past smoke signals. The signals they produce might be in frequency ranges we are not monitoring, might use principles of physics we have not yet discovered, might be so compressed and efficient that they look to our instruments indistinguishable from random noise. Think about it this way. Imagine a civilization that encountered Earth in the year 1500 before widespread radio communication. They scan our planet for signs of intelligence. They listen for radio signals. They find none. They conclude, incorrectly, that the planet is uninhabited. The absence of the signal they were looking for did not mean the absence of intelligence. It meant only that they were not looking in the right way for the right things. We may be making an equivalent error. In April 2026, researchers from the Earth Life Science Institute published a new method for detecting extraterrestrial life that does not rely on traditional biosignatures, the specific chemical signatures like oxygen or methane that we associate with biological activity. The new approach looks for patterns of chemical complexity that could not be produced by known non-biological processes. It looks for signs of order that only a biological system, any biological system, not just one resembling Earth's, would produce. It is a small step, but it matters. It represents a shift in the fundamental assumption from "we will recognize life because it looks like us" to "we will recognize life because it produces a specific kind of complexity regardless of its specific chemistry." The deeper problem is even more fundamental. We know one kind of life, ours. It is carbon-based, water-dependent, and operates within a fairly narrow temperature range. Those constraints are so built into our assumptions about biology that it is genuinely difficult to imagine life that doesn't share them. And yet nothing in the laws of physics says life must be carbon-based. Nothing says it must need liquid water. Silicon-based chemistry at the right temperatures produces complex molecules. Chemistry in liquid methane, like the lakes on Saturn's moon Titan, might sustain something metabolically functional. We are not looking for those. We don't know how. There is a sentence attributed to the philosopher Ludwig Wittgenstein: "If a lion could speak, we could not understand it." What he meant was that understanding depends on shared context, shared world, shared forms of life. A lion's experience of reality is so different from ours that even if it could produce language, the concepts behind that language would be alien to us. An extraterrestrial intelligence may be more different from us than a lion is, may process information in ways that produce no signals we recognize as signals, may communicate on timescales so long that its entire conversation with a neighbor takes place over geological time and any single transmission lasts 1,000 years, may have no concept of transmitting to the unknown, no impulse to announce its existence, no equivalent of the curiosity that drives us. The silence, in other words, might not be emptiness. It might be incomprehension. We may be listening for the wrong things. We may be listening at the wrong time. We may be listening with the wrong instruments for a signal in a language we have no framework to pass. That does not make the search futile. It makes it harder than we thought. It makes it larger than we thought. It makes it one of the most genuinely difficult scientific problems in the history of human inquiry. And it hands the Fermi Paradox back to us, not dissolved but deepened. The Fermi Paradox has generated a great many proposed solutions. Some of them are reassuring, most of them are not. Let us go through them slowly, because each one, examined carefully, says something different about the universe and about us, and one of them, the last one, is the most disquieting thing I know. The first class of solutions is called the rare Earth hypothesis. It proposes that while simple life, microbial life, single-celled organisms may be common throughout the universe, the conditions required for complex intelligent life are extraordinarily rare. Not just a habitable planet, but a planet with the right kind of star, the right kind of neighbor planets to stabilize its orbit and deflect asteroids, the right kind of magnetic field to protect its surface, the right kind of moon to stabilize its axial tilt and drive the tides. Every one of these conditions must be met simultaneously. Perhaps they rarely are. Perhaps Earth is genuinely unusual. Not a typical world, but an extraordinary convergence of unlikely factors that produced a stable environment long enough for intelligence to emerge. If this is true, the silence makes sense. We are rare, perhaps unique among complex life. And the universe is quiet not because civilizations destroy themselves, but because they barely arise. The second class of solutions involves the destruction of civilizations. There may be a great filter, a step in the development of intelligent life that almost nothing survives. This idea, first proposed by economist Robin Hanson in 1998, asks us to consider where in the chain from chemistry to communicating civilization the filtering is most severe. If the filter is behind us, if the hard step has already been cleared and complex life is simply vanishingly rare, then we may have already passed the worst. We may be survivors of something almost nothing else has survived. If the filter is ahead of us, if civilizations reliably destroy themselves before they become interstellar, then the silence is a warning, and our future is not as certain as we prefer to imagine. The question of whether the filter is behind us or ahead of us is one of the most consequential, unresolved questions in science. And the answer changes based on how common complex life turns out to be. If we discover microbial life on Mars, if it turns out that simple life arises wherever conditions permit, that is good news in one sense. The universe is teeming with biology. It is bad news in another. If simple life is easy and intelligence is still absent everywhere, the filter must be ahead. Something kills civilizations, reliably, before they get old enough to be noticed. The third class of solutions is stranger. In 2008, a Chinese science fiction writer named Liu Cixin published a novel called The Three-Body Problem, which contained a hypothesis so disturbing that it has since been discussed seriously in scientific literature. The dark forest hypothesis. It proposes that the universe is full of civilizations and that every one of them is silent for the same reason. In a universe of finite resources, any civilization that announces its existence to the cosmos is making itself a target. The rational response to receiving a signal from another intelligence is not to reply. It is to eliminate the sender before they can become a threat. Every civilization knows this. Every civilization stays quiet. The forest is full of hunters, moving in silence. This is not a scientific theory. It is a thought experiment. But it is not a frivolous one. The logic is internally consistent, and it has an implication that is worth sitting with. We have been broadcasting our location into space for over 100 years. If the dark forest hypothesis is correct, we made an announcement without understanding the room we were announcing into. The fourth solution, the quietest one, is the one I find myself thinking about most often at this particular moment in history. What if we are simply early? The universe is 13.8 billion years old. Our sun is 4.6 billion years old. In cosmic terms, our star is middle-aged. But many of the stars in our galaxy are older, much older, and many of the stars that will eventually produce habitable planets are not yet born. The universe is a long way from finished. Most of the stars that will ever exist have not yet lit up. Most of the habitable worlds those stars will eventually warm are not yet formed. We live, in other words, very close to the beginning of the universe's history of potential intelligence. What if the great filter is not destruction, but time? What if intelligence is not rare, but early, and we are among the first minds the universe has ever produced? What if the silence we hear is not the silence of a graveyard, but the silence of a universe that has barely started? If that is true, then every answer to the Fermi Paradox was the wrong answer. The universe is not empty because civilizations are rare. It is not empty because they destroy themselves. It is not empty because they are hiding. It is empty because it is young. We look up at a silent sky not because we are alone in a finished universe, but because we are early in an unfinished one. Consider what that would mean, not just for the question of other life, for our sense of our own significance. If we are early, if intelligence is just beginning in this vast and ancient universe, then the history of mind in the cosmos is, for all its billions of years of stellar evolution and planetary formation, barely underway. We might be, if not the first, among the first to look up and wonder. That thought, held long enough, becomes something that does not have a simple name. Every generation has asked this question, not in the scientific form, not with telescopes and equations and radio receivers, but in some form, in some language, under some conceptual framework. The question has been there, the thing that lies under all the others. Are we the only ones? The ancient Greeks debated it. Epicurus, writing in the 3rd century BCE, argued on purely philosophical grounds that an infinite universe must contain infinite worlds, and that those worlds must be inhabited. He had no evidence. He had no instrument that could detect the answer. He had only logic and the deep human resistance to the idea of an empty cosmos. Metrodorus, his follower, put it this way: to consider Earth the only populated world in infinite space is as absurd as to assert that in an entire field sown with grain, only one single seed will grow. He was reasoning from intuition, but his intuition was not wrong. In 1600, a Dominican friar named Giordano Bruno was burned at the stake in the Campo dei Fiori in Rome. Among his heresies was the claim that the universe was infinite, that it contained infinite stars, and that many of those stars had worlds orbiting them that might be inhabited by intelligent beings. He was not executed for this specifically. The historical record on his precise charges is complicated, but the Church made clear that his cosmological views were among the offences considered. He went to the fire without recanting. His views, by current understanding, were correct. In 1543, 57 years before Bruno's death, Nicholas Copernicus had published the work that removed Earth from the centre of the universe. The solar system orbited the Sun, not the other way around. It was a displacement, a cosmic repositioning that said, quietly but unmistakably, "You are not at the centre of this story." That displacement has been repeated several times since. With every new discovery, the universe has grown larger and our place in it more ordinary. We orbit an average star. That star sits on an unremarkable arm of an average galaxy. There are 2 trillion galaxies. The observable universe is 93 billion light-years across. We are not at the centre. We are not special by location. We are not even special by composition. Every atom in our bodies was forged in the cores of stars that lived and died before our sun was born. And yet, despite all of that, despite every step of that decades-long, centuries-long process of cosmic repositioning, the question persists. Not as a comfort, not as an insistence on our own importance, but as something more restless, a genuine curiosity that will not be settled by being told we are ordinary. Are we alone? Frank Drake asked it with a radio telescope in 1960. Jerry Amon heard something strange in 1977 and still doesn't know what it was. Hundreds of astronomers today spend their careers pointing instruments at the sky, searching for a signal that has not yet come. Undergraduate students are cataloguing habitable worlds. Mars rovers are drilling into ancient rocks looking for chemistry that only life produces. This is not a new question wearing new clothes. This is the same question Epicurus was asking, and Bruno, and every person who has ever stood under a clear sky and looked up at the number of lights there and tried for a moment to hold all of them at once. The science has changed everything about how we ask the question. It has not changed the question. And we are, right now, at the moment in human history when the science is beginning to be good enough to actually answer it, not theorize it, not philosophize it, answer it. The James Webb Space Telescope is probing the atmospheres of worlds around other stars. New observatories, including one named after Vera Rubin, are mapping the sky at resolutions previous generations couldn't imagine. New biosignature detection methods are being developed that don't rely on finding life that looks like us. Within the lifetimes of people currently alive, it is not unreasonable to expect an answer, not a certain one. Perhaps not a complete one, but a significant one. An answer to the oldest question we have. We have arrived, as every honest exploration of this question eventually arrives, at the place where science gives way to something else. Not to superstition, not to comfort, to something harder, to the specific weight that settles on a person when they have understood a question well enough to understand what the answer will mean. Let me lay out both possibilities one more time, as plainly as I can. If we are not alone, if there is, or has ever been, another intelligent species anywhere in the observable universe, then intelligence is not a freak accident. It is a feature, something the universe produces, under the right conditions, as a matter of course. The chemistry leads to biology, the biology leads to complexity, the complexity leads to a mind capable of looking back at the universe that made it. That sequence, if it has played out more than once, is not a coincidence. It is a tendency, something the cosmos does when left long enough with the right ingredients. And if intelligence is a tendency, then we are not isolated. We are part of something, a community of minds separated by distances that may never be bridged in any physical sense, but connected by having made the same journey, by having looked up at the same sky from different worlds and asked the same question. We would not be alone. We would be members of something, even if we never make contact, even if we never hear a reply. If we are alone, if in all of this vastness, in all of this time, only one mind has ever formed, then the universe made exactly one thing capable of knowing it, one set of eyes, one arrangement of neurons that can perceive the light from a galaxy 13 billion light-years away and understand what it is looking at, one voice in all of space, capable of asking the question we are asking tonight. That too is extraordinary, not in a comfortable way. In a way that has a specific quality of loneliness to it, a specific vertigo. To be the only intelligence in a universe of 2 trillion galaxies is to be both vanishingly small and irreplaceably large at the same time. Small because the universe has no obvious need of us, and large because without us there would be no one to notice it at all. Either answer requires something of you. Either answer requires you to adjust your sense of what you are and what this place is. Either answer says something about the significance of consciousness, of curiosity, of the particular kind of animal that builds radio telescopes and points them at stars, hoping. Here is the thing about the wow signal that I find myself returning to, long after I have moved past the technical details. Jerry Eman was not a famous scientist. He was a volunteer, going through printouts in his spare time, doing the quiet, unglamorous work of checking data that might not mean anything, and then, on a specific afternoon, looking at a specific page of a specific printout, he found something that had never been found before and has never been found since. He was paying attention, at the right moment, in the right place, looking carefully at something most people had walked past. That is the whole story of our search for life in the universe, in miniature. Not laboratories and laureates and triumphant announcements. Most of it is this: someone, somewhere, paying careful attention to something that might be nothing, and occasionally, rarely, finding something that might be everything. We are still paying attention, still listening, still looking. The sky has not answered, but the sky is wide, and we have only just begun to ask.